Quantum mechanics is the backbone of modern physics, explaining the behavior of nature at the atomic and subatomic levels. Imagine classical physics as a beautiful painting. It captures the big picture but misses the finer details. Quantum mechanics, on the other hand, zooms in to reveal the intricate brushstrokes. One of the most mind-bending aspects of quantum mechanics is wave-particle duality. Think of light behaving both as a wave and a particle. It's like light can't decide whether to be a ripple in a pond or a tiny marble. This duality is fundamental to understanding the quantum world. Now, let's talk about quantization. In classical physics, energy, momentum, and other quantities can vary continuously. But in quantum mechanics, these quantities are quantized, meaning they exist in discrete packets. Imagine climbing a staircase. You can only step on individual steps, not in between. That's quantization for you. Moving on to the uncertainty principle, an idea brought to life by Werner Heisenberg, it states that you cannot precisely measure both the position and momentum of a particle at the same time. The more accurately you know one, the less accurately you know the other. It's like trying to focus on both the wings and the beak of a hummingbird in flight. You just can't do it. Quantum mechanics didn't just appear overnight. It evolved from early 20th century efforts to explain phenomena classical physics couldn't, like black-body radiation and the photoelectric effect. Pioneers like Max Planck and Albert Einstein paved the way, and by the mid-1920s, great minds like Niels Bohr, Erwin Schrödinger, and Werner Heisenberg had developed the modern theory. The mathematical formulation of quantum mechanics is fascinating yet complex. Central to this is the wave function, a mathematical entity that provides probabilities for the outcomes of measurements of a particle's properties. But did you know it has been demonstrated to hold even for complex molecules with thousands of atoms? Yet applying quantum mechanics to human beings raises philosophical questions like Wigner's friend thought experiment, and its application to the universe as a whole remains speculative. Despite these complexities, the predictions of quantum mechanics have been verified experimentally to an exceptionally high degree of accuracy. For instance, quantum electrodynamics, or QED, refines quantum mechanics for the interaction of light and matter. It has been shown to agree with experiments to within 1 part in 10 circumflex 12 when predicting the magnetic properties of an electron. A fundamental feature of the theory is that it usually cannot predict with certainty what will happen, but only give probabilities. Mathematically, a probability is found by taking the square of the absolute value of a complex number, known as a probability amplitude. This is known as the Born rule, named after physicist Max Born. For example, a quantum particle like an electron can be described by a wave function, which associates to each point in space a probability amplitude. Applying the Born rule to these amplitudes gives a probability density function for the position that the electron will be found to have when an experiment is performed to measure it. One consequence of the mathematical rules of quantum mechanics is a trade-off in predictability between different measurable quantities. The most famous form of this uncertainty principle states that no matter how a quantum particle is prepared, it is impossible to have a precise prediction for a measurement of its position and also at the same time for a measurement of its momentum. Another fascinating phenomenon is quantum interference, often illustrated with the double-slit experiment. Here, a coherent light source illuminates a plate with 2 parallel slits, and the light passing through the slits is observed on a screen behind it. The wave nature of light causes the light waves passing through the 2 slits to interfere, producing bright and dark bands on the screen, a result that would not be expected if light consisted of classical particles. However, the light is always found to be absorbed at the screen at discrete points as individual particles rather than waves. This behavior is known as wave-particle duality. Electrons, atoms, and even molecules exhibit the same dual behavior when fired towards a double slit. Quantum mechanics also predicts phenomena like quantum tunneling, where a particle can cross a potential barrier even if its kinetic energy is smaller than the barrier's maximum. This has real-world implications, enabling radioactive decay, nuclear fusion in stars, and technologies like scanning tunneling microscopy and tunnel diodes. When quantum systems interact, they can create quantum entanglement, a state where their properties become so intertwined that describing the whole solely in terms of individual parts is impossible. This phenomenon enables quantum computing and is part of quantum communication protocols such as quantum key distribution and superdense coding. Contrary to popular belief, entanglement does not allow sending signals faster than light, as demonstrated by the no communication theorem. Another possibility opened by entanglement is testing for hidden variables, which would allow more exact predictions than quantum theory can provide. Many Bell tests have shown results incompatible with local hidden variables, reinforcing the uniqueness of quantum mechanics. Let's delve into its relationship with another cornerstone of modern physics, general relativity. Even though the predictions of both quantum theory and general relativity have been supported by rigorous and repeated empirical evidence, their abstract formalisms contradict each other and have proven extremely difficult to incorporate into one consistent, cohesive model. Gravity is negligible in many areas of particle physics, so unification between general relativity and quantum mechanics is not an urgent issue in those particular applications. However, the lack of a correct theory of quantum gravity is a significant issue in physical cosmology and the search by physicists for an elegant theory of everything, TOE. Consequently, resolving the inconsistencies between both theories has been a major goal of 20th and 21st century physics. This TOE would combine not only the models of subatomic physics but also derive the four fundamental forces of nature from a single force or phenomenon. One proposal for doing so is string theory, which posits that the point-like particles of particle physics are replaced by one-dimensional objects called strings. String theory describes how these strings propagate through space and interact with each other. On distance scales larger than the string scale, a string looks just like an ordinary particle, with its mass, charge, and other properties determined by the vibrational state of the string. In string theory, one of the many vibrational states of the string corresponds to the graviton, a quantum mechanical particle that carries gravitational force. Another popular theory is loop quantum gravity, LQG, which describes quantum properties of gravity and is thus a theory of quantum space-time. LQG is an attempt to merge and adapt standard quantum mechanics and standard general relativity. This theory describes space as an extremely fine fabric woven of finite loops called spin networks. The evolution of a spin network over time is called a spin foam. The characteristic length scale of a spin foam is the Planck length, approximately 1/161035 meters, and so lengths shorter than the Planck length are not physically meaningful in LQG. Both of these theories, despite their differences, aim to achieve the same goal: a unified understanding of the forces that govern our universe. Now that we've delved into the quest for unification between quantum mechanics and general relativity, let's turn our attention to the practical applications of quantum mechanics that have revolutionized modern technology and science. Quantum mechanics has had enormous success in explaining many of the features of our universe, especially at small scales where classical methods fail. It reveals the individual behaviors of subatomic particles, such as electrons, protons, neutrons, and photons, particles that form the building blocks of all matter. One of the most notable fields dependent on quantum mechanics is solid-state physics, which is crucial for understanding and developing new materials. Materials science, too, owes much of its progress to quantum theory. Modern technology often operates at scales where quantum effects are significant. Quantum mechanics has given rise to quantum chemistry, which helps us understand chemical reactions at the most fundamental level. Quantum optics explores how light interacts with matter, leading to advancements in lasers and optical amplifiers. Perhaps one of the most exciting applications is quantum computing. Quantum computers have the potential to solve problems that are currently intractable for classical computers, revolutionizing fields from cryptography to complex simulations. In the realm of everyday technology, quantum mechanics is behind the functioning of superconducting magnets, light-emitting diodes, LEDs, and transistors. Transistors, in turn, are the building blocks of microprocessors which power nearly all modern electronics. In the medical and research fields, quantum mechanics has enabled breakthroughs in imaging technologies such as magnetic resonance imaging, MRI, and electron microscopy. These tools provide unparalleled insights into the structures of materials and biological tissues. Even the very essence of life, DNA, can be better understood through the lens of quantum mechanics. The nature of the chemical bonds that hold together the molecules in DNA is rooted in quantum phenomena. Quantum mechanics isn't just a theoretical pursuit, it's a practical tool that continues to shape our understanding and capabilities in countless ways. As we continue to explore and develop this field, who knows what new applications and technologies await us?